Okay, so the first speaker of the afternoon session is Atul Sharma, who will tell us about celestial versus Carrollian charges.
Thanks, Andrea. I'd like to begin by thanking the organizers to give me the opportunity to come here yet again. This is my second time in Florence at a GGI workshop, and I gave the same talk last year, and I will give the same talk this year, so it's even more fun. There'll be some changes because I've learned a lot from my collaborators. So I'll be talking about work that I've done with Lionel, Rama, and one of Lionel's students, Adam Kmech. And the paper about this work came out last week, Monday or so, or Tuesday or so. So you can take a look at that if you want more details. So this project was supposed to be my temporary foray into the world of the symplectic geometry associated to asymptotic symmetries, which I was interested in studying by attending Andy's course on celestial holography and soft theorems that he gives at Harvard every spring semester. So in that course, as you have probably encountered in many papers in celestial holography, you learn that soft theorems associated with soft gluons or soft gravitons give rise to Ward identities. And those Ward identities get identified with asymptotic symmetries like the BMS symmetry in gravity and supertranslations, or the large gauge symmetries in gauge theory. And these symmetries have, is there an echo? No, right? Okay. These symmetries have an infinite parameter extension known as the S algebra, which was recently discovered by studying the soft collinear limits of gluon scattering amplitudes by Guevara, Strominger, Hemwich, Pate et al. And these symmetries have recently been reinterpreted in many different ways, including twistor space. And today I'd like to tell you a little bit about, well, I'll give a follow-up of Lionel's talk. So I'm assuming that Lionel gave you an overview of her paper. And I wanted to go into a couple of points in more detail that he may not have had the time to do. So I've talked to many of you over the last week or so. And the initial idea of this talk was just to give you a comparison between celestial and Carrollian charges. As in the Carrollian theory, the charges are charges that are conserved in Bondi time evolution, while in celestial CFT, the charges are supposed to be chiral currents that are holomorphic in Z bar evolution. But after talking to you, I've also realized that there seems to be a little bit of a missing link in the subject, in that the S algebra, beyond the usual large gauge symmetries associated with leading soft theorem, don't seem to have an interpretation, a rigorous interpretation in terms of asymptotic symmetries, at least from the viewpoint of space-time directly. So what I also want to talk about in this talk is try to give you an asymptotic symmetry interpretation of all of these, this whole tower of currents. So here I've written out the S algebra in a convenient basis where I've basically changed the notation a little bit, but otherwise it's a very simple commutation relation that looks like a Kac-Moody current algebra. So the generators of the S algebra are Lie algebra valued currents, JA, and I take modes of the currents, and the mode number is labeled by some integers R comma S. And they also belong to the wedge, by which in the subject it's meant that they're labeled by a pair of integers. So each generator J will be labeled by a pair of integers K comma L that will live in the positive real integers, non-negative integers, KL or Mn greater than or equal 0. And they'll satisfy a very simple commutation relation in terms of the Lie algebra structure constants FABC, which are the structure constants associated to the Lie algebra of the gauge theory that is under study. So in this talk, I want to focus on two different points. I want to show that this symmetry algebra is the asymptotic symmetry group of SD Yang-Mills, by which I mean self-dual Yang-Mills theory, in twistor space. And by this, I mean that I'll describe an action for this theory on twistor space, and then I'll give boundary conditions for the fields that live in twistor space, and soft gluon states will be states of those fields that will be precisely the states that are overleading with respect to those boundary conditions. And they will be pure gauge almost everywhere. So in that sense, they'll give rise to certain large gauge symmetries that I'll identify with the S-algebra symmetries. And the second thing is to build Noether charges, which is the main bit of what Lionel focused on. So what I'll do is I'll give you just an overview of the Noether charges, the final results for the Noether charges before I go into the main part of the talk. And then you can ask me questions if something confused you from today or even yesterday's talk. So Noether charges will be of two types. They'll come in two varieties. The first will be corner charges. Corner charges are the usual interpretation that you give to these asymptotic symmetries in the sense that they're charges that live on cuts of scry. They're integrated over the whole celestial sphere and are functions of U. And they're conserved or satisfy interesting flux balance laws as you take the U derivative. And the other type of charges that we will build are celestial chiral currents. And these charges will be integrals not over the whole celestial sphere, but over contours on the celestial sphere. So they'll resemble currents or modes of currents in a celestial CFT. So let me begin the talk by giving you the results for these charges, which can be stated purely in terms of quantities that live at null infinity without invoking twistor theory at all, contrary to what Lionel might have you believe yesterday. So the corner charges were constructed. So the corner charges for the extended tower of the S-algebra symmetries were constructed by Friedel, Pranzetti, and Ruclario. And then similar things have been studied by Laurent's student Nicholas Cresto as well, and Mark Gaylor and other people in the context of gravity. And there's a slow output of literature that's coming up building on these efforts. And it turns out that these corner charges, and I'm assuming that so Laurent gave a talk on this. You might not have been there, but I'll give you a summary of basically what he said. So what Laurent and friends do is they construct a bunch of charge aspects. So Laurent talked about the gravitational case, and I'm going to talk about the gauge theory case. So in the gauge theory case, you construct a bunch of charge aspects. These charge aspects are space-time quantities that basically constitute asymptotic data of space-time gauge fields and things like that. So for example, here J are integers greater than or equal to -1. And the simplest charge aspects that they construct are just large R limits of components. In this case, I'm taking self-dual or positive helicity components of the gauge field. So for example, R minus 1 is the large R limit of FUZ, and so on. R squared FCZ bar. R cubed FRZ bar. And the idea is that these so-called charge aspects fit into a very nice system of recursion relations, which take the form du rj plus curly dz bar rj minus 1 equals 0, which are recursions valid for j greater than or equal to 0, which basically determine the higher order aspects from the lower order aspects. And dz bar is the gauge covariant derivative on the celestial sphere, Z bar. So I have the leading large R component of the Z bar component of A in standard Bondi coordinates, UZ bar, or flat Bondi coordinates, as we use in the paper. And it will be convenient for the rest of the talk to just call this curly A bar, because this will be a recurring player in the game. For J equals 0 and 1, these are just the asymptotic Bianchi identities in full gauge theory. So you can take the Bianchi identity, d mu f nu rho epsilon mu nu rho sigma equals 0, expand it out and take its asymptotic limit. And you'd get this for j equals 0, 1. And for higher j, these identities receive corrections in general in full Yang-Mills theory. But it ends up that these do hold exactly in the self-dual Yang-Mills theory, in the sense that I can construct quantities solving these equations on the support of the self-duality equations. And I'll shortly tell you what self-dual Yang-Mills theory is, just giving the overview now. The idea is that once you have these charge aspects, you can construct S-algebra charges in the following sense. You can take an integral over a celestial sphere over a cut of scry at some given value of Bondi time. And the charge takes this general form. J runs from 0 to S, xi j rj. So this is the generic form of an S-algebra charge that FPR construct. I'm going to abbreviate the letters of these people's name by FPR because they're recurring characters. This is a generic structure of the charge. The data here is the data of the charge aspects. So the charge aspects are just general data, and then the charge is associated to a particular soft gluon.
Exactly the Newman-Penrose thing in the expansion in the case of gravity, or we're doing something a little different here?
No, interestingly, these are exactly the complementary things to the Newman-Penrose charges. So if you take, for example, one of these things, if you use one of these components, and do a large R expansion, then at each coefficient of R to some power, you get some coefficient which is a function on the sphere. You can split it into two pieces. One which is in the image of some derivative operator on the sphere, and one which is in the co-kernel, as in not in the image. Yeah. And the thing that's in the co-kernel can be extracted out by integrating over the sphere because it's not a total derivative term. So that gives a charge. And the thing that's in the image of the derivative operator on the sphere is these things, which like drop out when you do those nice spherical harmonic integrals that Newman and Penrose do to extract their charges. Like these things will actually sit in these expansions of, so the higher order quantities, R2, R3, and so on, FPR conjecture that they sit in the expansion of FRZ bar, this in the larger expansion of FRZ bar, with some derivatives acting on them, like something like partial Z to some power RS. And usually these are the things that drop out when you compute the, I can tell you more later. So this charge depends on the data of the general charge aspects, as Lionel would have discussed yesterday as well. And the data of the particular soft gluon symmetry that we are studying is encoded in some coefficients Cj. So both Rj and Cj are functions on null infinity, the joint valued functions in this case. And the sum here runs over 0 to some upper limit S, where S for a generator J, A, K, L, R is K plus L, which is basically identifiable with the order of softness in a soft expansion of the soft gluon, of a hard gluon, if you do scattering amplitudes. So the Xj's and the Rj's are basically, just as the Rj's here satisfied a recursion relation that was motivated using the asymptotic Bianchi identities, the Xj's also satisfy, or are postulated to satisfy, a recursion relation, which a priori is not clear where it comes from on space-time. This recursion relation will run in the reverse direction of the other recursion relation. So that's why FPR call it a dual recursion relation, which basically relates coefficient with J to something involving the C coefficient with J plus 1 index. Okay? And to construct the associated S algebra charge, or the mode for JAKLR will be constructed by taking this recursion and initializing it with the largest value psi s. We'll assume, or FPR assume, that psi goes up to j equals s, and after that you just set all the xi's to 0. So you take an ansatz for the largest value of psi, and to satisfy the recursion it has to be independent of u. So one takes psi s, where s is k plus l, to be minus z bar to the k, z to the minus r, where basically if you leave this as s, then k has to run between 0 and s. So the idea of FPR is that you start with this soft gluon generator. It turns out that this can be identified with the asymptotic data of a soft gluon in a trivial gauge field background. And these things, the lower order coefficient psi j, can be solved for using this recursion relation all the way down to psi naught. And those things are field dependent corrections that make sure that this charge is conserved or satisfies some flux balance law in the presence of a non-trivial gauge field background. So on the support of this set of recursion relation and this set of dynamical asymptotic Bianchi identities, these charges satisfy the following flux balance law, or the following conservation law, partial u q psi equals 0. Actually, I can write it as a flux balance law, where this becomes an integral over d to z of trace r minus 1 times the covariant derivative on the sphere of the lowest order thing, psi naught. And r minus 1 is the analog of radiation in the gauge theory case. Just like the news is the radiative data in the gravitational case, r minus 1, which is the asymptotic limit of FUZ, gives you the positive helicity version of the radiation in this case. And so one says that when the radiation vanishes, one has a conservation law. This is equal to 0 if r minus 1 is 0. So hopefully this is familiar from Laurent's talk. If you just substitute his gravitational charges, charge aspects by all these gauge theory charge aspects. Any questions about this?
Yes.
Yeah, is the other way to think about like conservation is like the charge matching at like I plus minus and I minus plus? Are there like a tower of antipodal matching conditions that this satisfies that will let you do that matching? Or?
So we haven't studied the conservation along spatial infinity here. That is a separate problem that actually we were discussing that we'll treat at some point. This is the conservation law that one would find once you're already at Scri plus minus. And then in a Carrollian theory in a putative Carrollian theory that might live purely on Scri plus, these will be conserved or propagate according to this flux balance law. So once you're already in the massless sector. And there should be a similar problem on Scri minus, and there should be an evolution problem on spatial infinity that maybe proves or requires the assumption of antipodal matching, but we haven't studied that properly. I don't know if Lionel wants to say anything more about antipodal matching. If you have any comments, you can mention. Or later is fine too. Yeah. That is for future work. Okay. So the second thing are the celestial currents. So these charges are functions of u. So they look like they're operators in some kind of extrapolate dictionary. They are operators that are dual to states that are dual to operators in a Carrollian CFT. Also, they evolve in u. So in that sense, there'd be a dual BRST charge that takes care of that partial u evolution. Okay. What we also want to do is make contact with celestial holography. And in celestial holography, it's not the U evolution that matters. Instead, you sort of do a non-compact compactification. You sort of diagonalize boosts, and you go to a different basis that is more appropriate to studying operators and currents that live on the celestial sphere. And the new result, okay, so that bit is basically what FPR did. One of the new results of our paper is that we can use the same ingredients to build celestial currents. And these take the following form. So just like Q psi is the corner charge corresponding to a S-algebra charge, you can build a chiral current in a celestial CFT, which is now a function of Z and a priori Z bar, because you have to prove its chirality. But let me not write Z bar explicitly. And it takes a very similar form. It's given by the integral over the null generators of scribe plus, which is a familiar operation when you go from Carrollian to celestial descriptions of the same kind of sums. And you get a trace of psi j times only a very simple modification. Well, there are only two modifications here. The integral over the cut is replaced by the integral over the null generators of psi, and the charge aspect gets a little offset by a -1. So that's the only difference. And now, using the same recursion and dual recursion relation, you can show that this obeys the following evolution law. Partial z bar jxi is the integral over du trace r minus 1. Again, you get the same kind of obstruction by radiation. And you also get a pair of boundary terms that for the purposes of this paper we have neglected, but let me write it out just because it's an interesting curiosity. We get a boundary term that takes the form j running from 0 to s, psi j rj, evaluated at scribe plus minus and scribe plus plus. So basically, in the absence of radiation, and if the fields obey some Schwartz-like boundary conditions so that these boundary terms die off at spatial and time lag infinity, we will get conserved currents of the celestial CFT. So this will give partial z bar jxi equals 0 if radiation vanishes plus appropriate boundary conditions. So the reason I'm not going to talk more about the boundary terms is because I'm going to derive these charges from twistor space, and uplifting these things to twisted space picks up some boundary conditions, which naturally turns this integral over the null generators into a contour integral, somewhat analogous to the discrete basis in celestial holography paper of FPR. And so the way these charges will come out will be as contour integrals over some complexified u direction. That's around the contour around u equals infinity. And in that sense, these will be chiral currents of the celestial CFT. And via the extrapolated dictionary, you would expect that these chiral currents are dual to certain S-algebra single trace operators in some large N-gauge theory that lives on the boundary celestial sphere. Here, the proper way to interpret it is as a celestial sphere that lives at spatial infinity. But okay, we won't need that detail.
Atul?
Yeah.
Is this supposed to be a current related to the leading soft theorem, or?
So each psi corresponds to a particular soft gluon. And so the leading soft gluon is, so psi is basically the data of this collection of coefficient psi j's, which run from 0 up to the order of softness s in omega to the s, in the sense.
Okay, I'm a bit confused because the whole tower of soft theorems has a conservation equation that has higher powers of z bar derivatives, and you seem to have only one.
Higher powers of z bar derivatives.
Yeah, like the subleading soft theorem will have dz bar squared on the current is 0, up to conduct terms, and so on.
I suspect I've already sort of defined, so dz bar squared of something is 0 is the same as dz bar of
Okay,
dz
so
bar
those
of
dz
something, yeah.
bars
Yeah.
will be inside the definition of your j.
Oh, I think so. I haven't thought about that, but I believe so, yeah. Because I can definitely show that these are in one-to-one correspondence with the soft gluons through a Noether charge
Okay, so
procedure. So it'll probably be some total derivative term that comes out, maybe. As in some kind of descendants or some multiple descendants, yeah. I don't know, Rama, do you know this? Okay. Okay. So, in the second half of the talk, let me tell you. Okay, so this is the comparison between celestial and Carrollian charges that I wanted to do. In the rest of the talk, I want to basically impress upon you that the S-algebra charges, the S-algebra symmetries are genuine asymptotic symmetries in a very canonical sense. But to see how, you have to go to twistor space. I'm so sorry. If you don't like it, you can remove my name from the list of people who get steak or something. Okay. So, as Anil would have gone over, to understand these things as large gauge symmetries, you work with twistor space. How do I want to? Yeah, okay. So twistor space, or maybe the projective space definition is better. Twistor space is complex projective 3 space. This has coordinates ZA, which one usually splits into a coordinate lambda alpha. So these are homogeneous coordinates. One usually splits it into a pair of spinorial homogeneous coordinates, lambda and mu. And then one removes the locus, lambda alpha equals 0, which corresponds to a line, which is known as a line at infinity. So what we'll do is we'll study self-dual Yang-Mills theory and we'll uplift it to twistor space. And the removal of the line at infinity creates a boundary in twistor space. And when we give boundary conditions of the fields of self-dual Yang-Mills theory at that boundary, the things that will violate those boundary conditions will precisely be the S-algebra generators. So, okay, there's a correspondence between points x alpha alpha dot in Minkowski space, M4, and lines Lx in twistor space, which is given by Penrose's incidence relations. Okay. So points in space-time basically map to copies of lines. And these are projective lines, so topologically they're copies of Riemann spheres. Okay? So this is X, this maps to a copy of a line Lx. The power of twistor theory is that self-dual gauge theory and self-dual gravity can be made to manifest their integrability by uplifting them to twistor space. In the sense that once you uplift them to twistor space, the things lose all their hardcore PDE behavior and they just become ordinary algebraic things that you can solve for. Self-dual Yang-Mills theory, ST Yang-Mills theory, is just a theory given by the action B wedge F minus. So you have some gauge field A on space-time, which is valued in some Lie algebra G over M. And B is an anti-self-dual two-form Lagrange multiplier field that imposes the self-duality of A in the sense that the equation of motion of B gives you F minus equals 0, where F minus is just F minus Hodge dual of F over 2. So it tells you that on shell the gauge field has a self-dual field strength. And the equation of motion of the gauge field itself, which sits inside F has its usual expression. The equation of motion of the gauge field tells you that B is a two-form that satisfies the Bianchi identity. And the asymptotic Bianchi identities end up being components of this Bianchi identity on B for the positive helicity case. Now this thing uplifts to a theory on twistor space. So twistor space is this real six-dimensional manifold P3. And the equations of motion of this action on space-time, the solutions of the equations of motion are in one-to-one correspondence with the solutions of an action of a theory on twistor space. Omega wedge trace little b wedge d bar a plus a squared. So just like we had the fields capital A and capital B on space-time, one has a theory involving two fields, little a and little b on twistor space, which are in one-to-one correspondence. And omega here is a volume form. So this is a holomorphic BF theory on twistor space. Omega is a holomorphic volume form, which looks something like this, where I choose to work with affine coordinates z, which is lambda 1 over lambda naught, and mu naught and mu 1 are sort of affine coordinates with the same choice of patch, lambda naught not equals to 0. And d bar is the anti-holomorphic derivative in these twistor coordinates. Okay. So the fields A and B here are also one forms. A plays the role of the gauge field on twistor space, and you should think of it as a proxy for the positive helicity degree of freedom. And B plays the role of, maybe I should, okay. B plays the role of the uplift of capital B, which is the Lagrange multiplier field, which you should think of as the negative helicity degree of freedom. And the idea is that solutions of the equations of motion, so the equations of motion on twistor space are very simple. You get an equation that says that the following deformation of the d bar operator, d bar plus a, is an integrable deformation, as in its connection is flat. And the other equation of motion is the equation of motion of A, which tells you that B satisfies a similar Bianchi identity. So these are just completely identical to the space-time equations of motion in their looks. And there's a theorem by Ward, built on a lot of work by Penrose, of course, that there's a one-to-one correspondence between solutions on twistor space of these equations and solutions of the equations of motion of self-dual Yang-Mills theory on space-time of Minkowski space. Just a subtlety that in Minkowski space, these solutions are necessarily going to be complex valued. So if somebody is less comfortable with that, you can also work in 2,2 signature where things have nice reality conditions, or Euclidean signature. Okay. Now, I'm only going to write the correspondence in terms of data on scry, because that's the data we need to generate asymptotic symmetry charges. So on shell, I can go to a gauge. I'm allowed to solve the equations of motion because I'm building classical Noether charges. So on shell, I solve the equations of motion, which allows me to go to a gauge that is adapted to null infinity. So I'm going to go to radiative gauge, where little a will take the form of a bar dz bar. Now, what have I done here? In order to do this, I need to make an identification between some of the coordinates on twistor space and the coordinates on null infinity. That can be done using a very clever formalism called the asymptotic twistor space. The asymptotic twistor construction is basically just a coordinate transformation. Up till now, I've been using coordinates mu, alpha dot, and z on twistor space. But it turns out that twistor space has a very natural fibration over null infinity, which also helps you visualize what twistor space is. So suppose you have null infinity that looks like your favorite cone. There are coordinates that go up the generators of null infinity, and there are coordinates z and z bar that go along the celestial spheres. The first step is to complexify null infinity, which means that you simply extend u to run over all complex numbers rather than just the real generators. And the second step is to consider a projection from twistor space onto scry C. And this projection is simply given by taking the coordinate z on twistor space and identifying it with the coordinate z on the spheres on null infinity. So z just goes to z. And then the mu alpha dots, they go to the following value of u. Mu lambda bar over, you can choose some affine coordinate. Say we work in the patch lambda naught not equals to 0, so you choose some affine coordinates. And this combination basically is needed to remove the homogeneities in mu and the complex conjugate lambda bar. So this gives you a map from PT to scry C. So basically, in pictures, it just looks like twistor space is null infinity with a rank 1 vector bundle over it. And the fibers of this vector bundle are copies of the complex plane C. And let me take the coordinate on this complex plane. Let me call it Q. Okay? Or you can take any coordinate, any convenient coordinate on this space. And I'm going to choose the coordinate Q on this space to be simply mu1 dot over lambda naught. So it's just some choice of affine coordinate on that, on the fibers of that geometry. What this allows us to do, so basically in summary, PT roughly looks like scry C times an extra complex direction, very simple. And what this allows us to do is, now that we've identified Z on PT with Z on scry, I can take radiative data on scry, which was just the A bar component, the large R component of AZ bar. And I can simply pull that radiative data back to PT. So all this is to say that the one form, little a on twistor space associated to a particular gauge field background on space-time is just given by its asymptotic radiative data. That's all you need to remember. Little a is just the asymptotic radiative data, which is simply something that comes from null infinity. Similarly, you can recover, so you can also go the other way and you can recover, if you have a general A given, there's a gauge symmetry that you can use to bring it to this form on twistor space, and you can recover the asymptotic data like that. Similarly, you can recover this negative helicity space-time field as well by doing something called a Penrose integral transform, for which also you need to do some gauge fixings that I won't discuss. Okay, so that's the connection between the theory on space-time and the theory on twistor space. And the broad brush utility of this construction is that once I've reformulated everything as a theory on twistor space, I can play the same covariant phase space games that people like to play on space-time, but on twistor space. So as I said earlier, I can create a boundary in twistor space. So let's give some boundary conditions because this theory has to be well-defined. So what boundary conditions should we give to the fields of this twistor space theory? The boundary was given by the line lambda alpha equals 0 that I removed. Now, projectively, the projective equivalence class of Z is an overall projective equivalence class of mu and lambda. So sending lambda to 0 is equivalent to sending mu to infinity, while holding the ratio of mu's fixed. So basically, this gives you a complex two-fold boundary. So you get twistor space, which looks like some lines, 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 and then as you go out to infinity, you get a line that is given by mu alpha dot equals infinity. There's some line that corresponds to the origin of space-time, which is mu alpha dot equals 0. So there's a boundary of twistor space, and our holographic dual should live at that boundary, is the conjecture. So let's study the boundary conditions. Since we have said that mu alpha dot equals infinity is the boundary, we can translate this into the coordinates u, q, z there are coordinates that come from null infinity. So the coordinate transformation that maps null infinity coordinates into twistor space coordinates is remarkably simple. It's simply lambda alpha is just 1 comma z, and mu alpha dot is u minus qz bar and q. So mu alpha dot going to infinity quite nicely gets identified with the boundary at u going to infinity. This gets identified with the boundary as u goes to infinity. So I'm considering a real boundary. So this is as the magnitude of u goes to infinity. I also have to send the magnitude of q to infinity, and I have to hold the ratio of u over q fixed, or the magnitude of this ratio. So basically, physically speaking, going to the boundary of twistor space is the same thing as going to the boundaries of null infinity, which are the points at infinity. So this tells you why this is the right kind of boundary to look at in twistor space.
Sorry, if u goes to minus infinity, then mu alpha dot goes to minus infinity. What's that here? In the drawing, there is no minus infinity.
Right, I just drew it as, it's like a connected boundary. It has one, minus and plus get connected if you just complexify u, right? Just, yeah, anyway. I don't need to pull this up. Okay, so now let's give boundary conditions. The choice of boundary conditions comes from the physical, as always, if we want to give boundary conditions, we have to ask ourselves, what is the physics that we want to recover? We want to recover the physics of soft gluons, so it's only natural to try to give the the simplest boundary conditions that is strict enough that it makes all soft gluons overleading, but does nothing worse. So we'll do that. It turns out to be very simple. All we need to do is impose the boundary condition that these fields fall off at basically the fastest rate that they can as u goes to 0. So I will impose the boundary condition that a goes to 0. So a has a first order 0 at u equals infinity. So basically I'm saying that a goes like order of 1 over u. And I'm going to assume that all my fields are analytic, at least on shell. I'm not going to consider the log u terms that show up at quantum level. Similarly, there's a boundary condition on B that basically gets determined by its weight, which says that it can have a third order pole at u equals infinity, but no worse pole. But that boundary condition is not going to be. So we also, this is a bit sloppy, so we give a bit more careful construction of the boundary conditions in the paper that you can look at. And this boundary condition goes into the construction of the positive helicity charges. There's a completely analogous construction of the negative helicity charges using the boundary conditions on B. Okay.
Sorry, are they sufficient so that the symplectic two-fold is finite?
Yeah, or at least the charges I'll construct will be finite.
So not necessarily the symplectic two-form. You're only interested in finiteness of the charges.
Actually, no. The symplectic two-form is, so the symplectic two-form will be finite. Yeah, okay, sorry.
Okay.
If
Thank
the
you.
charges are finite, it's actually stronger than the symplectic two-form being finite, because the symplectic two-form is this thing. This will be finite if both B and A satisfy the boundary conditions. What I'm going to allow is that one of them not satisfy the boundary condition, and the thing will still be finite. So it'll be even better, which is what you want if your charge should be finite. Yeah, this is finite. Otherwise, that would be very sad.
Well, it was just not trivial for your UQ. That's why I was asking.
It becomes trivial because omega carries some pole or something like that. It all gets determined from the homogeneity weights of these things. Like if you were studying a standard BF theory, a holomorphic BF theory, then both of these would have 1 over u poles, but it's because of that weight of B. Okay, so now, okay, I'm going very slowly. Now let me tell you at least the definition of large gauge symmetries. So what I'm going to do is I'm going to use the twistor structure to give a radial quantization of celestial CFT. And twistor space allows us to pull off that radial quantization into a radial quantization of the 6D self-Julian Mills theory. Twistor space has the structure of a vector bundle. You can show that P3 minus that copy of the line at infinity is biholomorphic to the total space of O1 plus O1 over P1 with coordinate Z. And the mu's can be interpreted as fiber coordinates on these O1s. Using this structure, what we do is we say that the celestial CFT lives on this base P1, and then the fibers just come along for the ride. So when I do radial coordination on this base P1 sphere, that radial coordination is just coordination along contours of constant mod Z on that sphere. This uplifts to a coordination of the bulk theory, where I basically choose my Cauchy surfaces to be these. So basically each point on this sphere is a copy of the fiber C squared of this rank 2 vector bundle and has coordinates mu0 and mu1. Radial coordination chooses contours on the sphere for coordination, and it chooses 5 real dimensional surfaces, which are products of this copy of C squared times this contour on the sphere. So this picks up a Cauchy surface for this 6 real dimensional theory that lives on Twistor space. Now, what we do is we define, when we quantize a theory, when we quantize a 2D CFT, what do? We start with a sphere, and we remove the points at 0 and infinity, and we define, we quantize on the resulting cylinder. So this motivates a definition of large and small gauge symmetries. So at infinity, you place in and out vacua. A large gauge symmetry should be something that is allowed to change those vacua, while a small gauge symmetry should not. So we say that a large gauge symmetry, oh, sorry, I forgot to actually tell you what the gauge symmetries on Twistor space are. But let me first say, large gauge symmetry will be a symmetry, well, this will preserve my boundary conditions in U away from Z equals comma infinity. A small gauge symmetry will be a gauge symmetry that preserves boundary conditions in U everywhere, including Z equals 0 comma infinity. And the asymptotic symmetry group will be the group of large modulo small gauge symmetries. Okay? So this is how I will define my asymptotic symmetry group, subordinate to the radial coordination of celestial CFT. So I forgot to tell you what the gauge symmetries were. So let me just tell you the gauge symmetry that generates the S algebra charges. There are 2 gauge symmetries in this theory, and one of them is just the standard gauge symmetry of, yeah.
So this is like the asymptotic symmetry group of like gauge symmetries in Twistor space. But on space-time, we're really talking about like all of the possible deformations of the field, right? Like many of these will change F mu nu, right?
These will change F mu nu. Yeah, these will.
Right. So
these will, well, there'll be a space-time phase space, and these will take you outside of that phase space.
right. I'm just right. So most of these transformations are like adding in radiation.
Yeah.
Right. Okay. Thank you.
Yeah, adding in soft gluon radiation of different soft orders. Yeah. So the gauge transformations of interest are these gauge transformations that just correspond to rotations of the frames of the Yang-Mills bundle, where psi is the gauge parameter. Psi is some adjoint valued gauge parameter on Twistor space with homogeneity 0 in the Twistor coordinates. And what the boundary conditions, right, I think 8 minutes. What these boundary conditions are telling you to do is a gauge transformation that preserves the boundary conditions will have to die at u equals infinity. So it's simple to what to do. You know what to do. You simply take those gauge transformations that don't die off, that grow as u goes to infinity. And the basis of such gauge transformations is given by things of this form. So things that grow as mu naught and mu 1 go to infinity. And okay, so I didn't explain this point, but you also have the freedom to remove any small gauge transformation. So once you take account of this quotient by small gauge transformations, the things that are left are precisely generators that are in one-to-one correspondence with the S algebra. So these are things that grow as mu naught or mu 1 go to infinity, and they're allowed to be Laurent in Z. So basically the idea is that if you're in a trivial background, you act on this with a d bar. The d bar picks out the derivative of a delta function supported at z equals 0 or z equals infinity, depending on what r is. And that tells you that this gauge transformation is supported exactly in small neighborhoods of 0 and infinity, which you can accomplish using this quotient by small gauge transformations. Okay, so this is the kind of basis of generators you find. And now, suppose I call this psi KLRA. Okay? The algebra of these gauge transformations is subordinate to the simple Lie algebra bracket. And already at the level of these generators, you see that if you compute just the Lie algebra bracket and think mu naught, mu 1, and z as just auxiliary variables that you can freely multiply, then you simply get, so suppose this comes with a TA, this comes with a TB. These are some Lie algebra generators of the Lie algebra math frac G. And the other things you just freely multiply. So you get K plus M, L plus N, or Z to the R plus S. And this is exactly F, A, B, C. You get a TC, which combines with this thing and turns into the S algebra, the soft gluon that comes out on the right-hand side of the S algebra. So this is how you recover the S algebra as the asymptotic symmetries of Self-Yang-Mills theory in twistor space. Let me just say that, just write a couple more equations to show how the charges come out. Since Lionel already did this in some detail, I'm assuming people have got a flavor of this at least. But to construct the charges, you start with the action of the theory on twistor space. You do another procedure on that with these boundary conditions, and you get a charge. Let me do the celestial charge case since I've already discussed the celestial Cauchy surfaces. The charges that come out will be, so originally there'll be contour integrals along the Z sphere and integrals in the mu directions. So they're corner well, okay, let me just write the integral over, so I'm assuming that you're familiar with the fact that gauge theory, large gauge charges are corner charges in that they localize on codimension 2 surfaces. So if you take a Cauchy surface sigma, which in my case was that circle times the c squared fibers, then the charge localizes on the boundary of that Cauchy surface. And it simply takes the form of the gauge parameter xi times the canonical conjugate to A. So this is a gauge transformation of little a, basically. So it's generated by little b, which is the canonical conjugate to A on twistor space. And this thing looks like dz, the contour integral in dz, an integral over du dq. So these things come from the volume form omega here when you plug in the coordinate transformation to scry coordinates. And then you have psi with b. So basically what happens is that you take psi, which on twistor space is a function of u, z, and q. And using the holomorphy, so there I wrote the answer for the large gauge soft gluon mode in a trivial background. to get a nonlinear expression that includes both the soft and hard pieces of the charge in the fully non-abelian theory, you actually have to correct that expression mu naught to k, mu 1 to the L by field-dependent corrections. Those field-dependent corrections usually take the form of an expansion in Q, where the expansion runs up to the order of softness S, which in that case is K plus L. And these things, using the small gauge quotient, you can demand that the gauge transformation d bar psi only has support at z equals 0 and z equals infinity. So you can demand that d bar psi is 0 away from z equals 0 and z equals infinity. This definition of large gauge transformations is exactly the thing that reproduces the dual recursion relations that were found by Friedel, Pranzetti, and Ricciardo. So I went over this quite fast. I invite you to look at the paper for the details. It's very simple, just coordinate transformation. It's like delightfully simple how the soft gluon generators come out by simply demanding this simple celestial holography-inspired definition of large gauge transformations. You plug this in, and you get the charge aspects coming out as well as some integrals over Q that I won't write because Lionel already wrote them for you yesterday. Okay, thank you very much for listening.
Questions?
So related actually to the previous question, you don't have any Schwarzian fall-off condition to impose here? You don't have any like Schwarzian type kind of fall-off to impose on your fields on twistor space because you don't do integrals over scry anymore? Is that the reason, or?
The fall-offs on twistor space are just the minimal fall-offs that we needed to make all the soft gluons overleading and nothing more. So
you don't see an analog of this Schwarzian fall-off that you have in space-time?
No, we do, in the sense that we do assume that our things, all our fields are, on shell, all our fields are power series in 1 over U.
Okay.
We do assume that. Yeah. So, for example, we don't allow log U terms.
If you did really BF theory as opposed to self-dual Yang-Mills, you should have way more gauge symmetries, right? How do you see those in twistor space? You know, like the symmetry of BF theory.
Well, this theory uplifts to a holomorphic BF theory in twistor space. An actual BF theory is a topological theory. I'm not entirely sure how to uplift it to twistor space, just because I've never tried. It seems simple enough that it might be doable. But the other thing is you might just be able to directly get the charges on space-time at that point.
Well, surely what we have, it's not completely analogous, but I mean, it's the J tildes, which are really the gauge transformations of the B. So it's not a shift symmetry of the B. It's
oh yeah, there's an entire separate tower of J tildes.
That's right. And so that's what's hard to see on space-time.
It's in the paper, so I didn't discuss it here. But there, you replace B with little a, and there's another gauge symmetry that they generate. And there should be something similar if you just directly try to do it on space-time with a normal BF theory.
A comment to Simona's question. So the S algebra and W algebra charges correspond to topological charges in celestial CFT, while the class of all asymptotic symmetries, sort of from the codimension 1 perspective, is much larger. Any more questions? If not, then let's thank Atul again.